The deepest human drill into the Earth's crust stopped at a depth of 12,262 meters. The diameter of the Earth is 12,742 kilometers, or 12,742,000,000 meters. So, have you ever wondered how scientists know that the Earth has a solid core, composed mainly of an iron-nickel alloy? Before we delve into the core, let's understand the overall structure of the planet. Mechanically, the Earth can be divided into three main layers: the crust, the mantle, and the core. The core comprises two parts: an outer core, which contains liquid iron and nickel, and an innermost solid core. The solid core has a diameter of about 2,440 kilometers, constituting around 20% of the Earth's total diameter. This makes it approximately 70% of the Moon's diameter. Encircling the solid core is the outer core, with a thickness of approximately 2,260 kilometers. The mantle can be subdivided into the upper mantle and the lower mantle. The lower mantle, extending to around 2,240 kilometers deep, is solid and composed of rocks and minerals, forming a crucial layer between the core and upper mantle. Above it, the upper mantle spans 35 to 660 kilometers, playing a fundamental role in Earth's geology and plate tectonics, driving the movement of continents and oceanic plates. Above the mantle lies the Earth's crust. Contrary to its massive size, the crust is surprisingly thin, measuring between 5 to 10 kilometers beneath the ocean floor, and up to about 70 kilometers on continents. On average, the Earth's crust is approximately 40 to 45 kilometers thick, representing a mere 0.3% of the planet's entire volume. Imagine if the Earth were an apple. Its crust would be as thin as the apple's skin, and we humans would be like tiny bacteria living on its surface. Although we haven't drilled through the apple's skin, we have concluded that this apple has 6 seeds. Do you see the similarity? We make conclusions about the structure of the Earth as if we have cut it in half and seen what's inside, even though we haven't fully explored its thin outer layer. However, it's important to note that scientists cannot fabricate data like that. The question remains, how did they study the Earth's structure to know that our planet indeed has a solid core inside? Have you ever wondered why the deepest human drill stopped at a depth of 12,262 meters? This depth represents the deepest point of the KOLO super deep borehole, which is also the deepest artificial point on the planet. The KOLO super deep borehole was a remarkable scientific endeavor by the Soviet Union, located in the remote KOLO Peninsula near the Russia-Norway border. Its mission was to penetrate as deep as possible into the Earth's crust. In 1979, the project made history by breaking a world record, reaching 9,583 meters. In 1982, it reached 11,662 meters. A second borehole was initiated at 9,300 meters from the first one and surpassed 12,000 meters by 1983. Unfortunately, on September 27, 1984, a section of the drill pipe, about 5 meters long, twisted and broke, leaving it behind at a depth of 12,066 meters. The project was restarted in September 1986 with a third borehole at a depth of 7,000 meters from the first borehole. By 1990, it had reached 12,262 meters, the deepest point of the entire project. Despite further attempts with the fourth and fifth boreholes, funding shortages led to indefinite suspension in 1994, with the project's deepest point remaining at 12,262 meters. At a depth of 12,262 meters, the KOLO super deep borehole penetrated approximately 1/3 of the continental crust's length. It unearthed a vast amount of geological data, showing how limited our understanding of the planet still is. One of the most fascinating discoveries from the KOLO super deep borehole was the finding of well-preserved microfossils at a depth of over 6 kilometers within rock layers dating back to more than 2 billion years. However, it did not provide evidence of a solid core on the Earth. The credit for this discovery belongs to seismic waves. Seismic waves are energy waves that travel through the Earth, primarily released during earthquakes, volcanic eruptions, or large artificial explosions. By leveraging the changes in the propagation speed of seismic waves through different mediums, seismologists have used them as a tool to study the structure of the Earth without physically drilling down to its core, a desire they have but cannot currently achieve. Seismic waves are detected by a seismometer, which typically consists of a time-measuring device and a recording machine. The data obtained from this instrument produces seismograms, revealing the location, earthquake intensity, and internal structure of the Earth. In this video, we will focus on two types of seismic waves: primary waves, known as P waves, and secondary waves, also known as S waves. P waves are a type of longitudinal wave that are the fastest among seismic waves. They have the ability to travel through any material, including the Earth's interior, and they are the first waves to be recorded by seismometers during an earthquake. In the air, P waves take the form of sound waves, traveling at the speed of sound. Their average speed in the air is approximately 330 meters per second, while in water, it's about 1,450 meters per second, and in granite, it reaches around 5,000 meters per second. On the other hand, S waves are slower than P waves. They're transverse waves, meaning they move horizontally. But there's a catch. They can only travel through solid materials. When they hit a liquid layer, the boundary between Earth's mantle and the outer core, they get thrown off track. This peculiar behavior gave scientists a puzzling idea about the Earth's core. They once believed it to be a uniform molten sphere. What makes P waves distinct is their ability to penetrate through almost any substance. When a P wave originates from one end, it can appear at the opposite side of the Earth. Seismologists can utilize the known structure of the Earth, including the crust, mantle, and hot molten core, to calculate the speed and position at which P waves will be detected on the other side of the planet. However, it's important to note that P waves don't always arrive at the expected location. Similar to light waves, seismic waves, particularly P waves, undergo refraction when transitioning from a solid medium to a liquid medium, and vice versa. When P waves travel from the solid mantle to the liquid outer core, they refract and change direction. Seismologists take this refraction into account while calculating where the P waves will emerge. But sometimes, P waves re-emerge at a different location. This unexpected behavior suggests that something must have caused the P waves to change direction once again and appear at a different location than anticipated. The most plausible explanation for this phenomenon is that the Earth's core is a solid sphere with a diameter of about 2,440 kilometers. And that's how scientists discovered the solid core of the Earth, using seismic waves. Nowadays, scientists use various other sources to collect information about the Earth's solid core. But that will be the subject of another exciting video. Thank you for joining us on this journey of discovery. If you enjoyed this video, don't forget to hit that like button and subscribe for more interesting content. Stay curious and keep exploring.